Let's take a look at problem 17.1. In this problem here, we have a simply supported steel shaft, so let us know made of steel. In the figure shown below here, this is connected to an electric motor with a flexible coupling, so we have a flexible coupling there, and they ask us to find the value of the critical speed of the rotation of the shaft. Now in the given diagram, we also have some more information here. We have that our shaft diameter is given to us as 0.25 inches, and that the distance, or the total length of the shaft that we're dealing with here between the two supports, is going to be 20 inches. So now they've had a chance to read through the problem statement, look at the given schematic, and see what they're asking us to solve for. The next thing we want to do is write down in a clear, concise manner everything that they tell us in that problem statement, what our variables are, our values, how they relate to our problems, what units we're using, a slightly simplified diagram, what they're asking us to solve for, and any assumptions that we're going to make in order to solve this problem. So, what do we know? We know it's a steel shaft. We know it's simply supported. They tell us there's a flexible coupling. They also give us the diameter of the shaft is equal to 0.25 inches. They tell us that the shaft length is 20 inches. Here's our given schematic here, simplified a little bit. There's our motor, flexible coupling. We have our 0.25 inch diameter shaft. We know the shaft length between the supports is 20 inches. And we know that they're asking us to find the value of the critical speed of rotation of the shaft. So from that information there, we should be able to choose some key equations in order to begin the solution of the problem. But before we get there, what we also want to do is come up with our basic assumptions. So the things we're going to assume to simplify down the solution to our problem is, one, we're going to assume that the bearing friction is negligible, so we're not going to be dealing with any friction forces. The bearings supporting the shafts are accurately aligned, so we're assuming the alignment is correct for all of this. And lastly, we're going to assume that the shaft remains linearly elastic. So now that we have all that information down, the next thing we can do is start our solution. So for our solution here, the first thing we want to do is look for some governing equations to start with. So the first place we want to start is we're going to head to Appendix D2 in the back of our textbook. So now we head to Appendix D2 in the back of our textbook. This is our shear moment and deflection equations for simply supported beams. So now what we want to do is look through this whole chart here and decide which case best matches us. So what we know here is we have a uniform load. So we're down here in case 3, and we're looking for maximum deflection. So we come over here from uniform load. Yes, we have the two support pieces on the end. We have this length L here. And at the maximum deflection, we now have this relationship here, which is given to us as 5W L to the 4th over 384 times EI. So here's our equation here that we got from Appendix D2. We write that here. Our delta sub ST is equal to now 5W L to the 4th over 384 EI. And again, this is for a uniform load distribution. So within this here, we say, okay, I know I'm going to need a couple more of these variables. One thing I know that I'm going to need for sure is my modulus elasticity and my I value here. So what we can do is we can go to Appendix C1 and B1 to get these two values. And when we do that, we go to C1, we can get our modulus elasticity equal to 30 times 10 to the 6. And then if we go to Appendix B1, we get our I is equal to this relationship here, our pi d to the 4th over 64. So now let's take a look at Appendix C1, and then we'll go to B1 and see where we got these values and relationships from. So now we head to Appendix C1 in the back of our textbook. Here, this is a table for the physical properties of common metals. So we can go back to the problem statement and realize, okay, our metal that we're dealing with is a steel. So if we're dealing with a steel here, we can come over, and we're left now, if we look on the top here, modulus elasticity, modulus rigidity, all these other different values here, but what we're concerned with is our modulus elasticity, our E value here, we're dealing with units of PSI. If we're dealing with English units, we deal with this column here. But again, make sure we note this is mega PSI. So we have 30 mega PSI for our modulus of elasticity of steel. So now we head over to Appendix B1A, properties of sections here. Sections we're dealing with now is a circle, known diameter D here. We can come over to the right now, and we can get our moments of inertia of I, and again we pay attention to the units of this here, inches to the fourth. So I is equal to pi d to the fourth over 64 in units of inches to the fourth. So with the equation that we just got from our appendix, our moment of inertia here, rewrite our equation again. I is equal to pi d to the fourth over 64. Again, remember we're in units of inches to the fourth here. So we can plug in what we know. Well, we know our d is given to us as 0.25 in inches. So units are good so far. We can plug this in here. So I is equal to our pi times 0.25 to the fourth all over 64. Do our math here. We get a value for a moment of inertia here. I is equal to 1.92 times 10 to the negative fourth in units of inches to the fourth, which is correct. So with this information that we gather now from our moment of inertia and that equation from our appendix, we can go back to this relationship that we have here, plug in our values that we know. So what do we know? We have W, L, E, and I over here. So I now come over here to the right and write down the values for everything that I know. Well, the first thing we know is we know our L value here is 20 given the problem statement in inches. We looked up our E from the back table is 30 times 10 to the 6. Our I value we just solved for above here for a moment of inertia is 1.92 times 10 to the negative fourth. We can look up our rho value here for steel in the back of our textbook here, and we find that this is 0.28 pounds per inches cubed. And we see that we do need to solve for our W. We look up our relationship for W. W for this particular problem here would be given by A times rho, our density there, which is equal to pi d squared 4 for area times our rho value there. So then what we can do is we can come down here, plug in to this relationship here, our d value here, which is pi now d squared there, all over 4 times our density over here. Our rho is 0.28. Again, from the lookup. So we do this out here, and we now get a value for our W of 0.0137 pounds per inches. So now we can go back to our governing equation here. We realize, okay, now we have a value here for W, we have a value for L given the problem statement. We looked up our modulus of elasticity, and we looked up our moment of inertia here. So we have all of this now that we can plug and chug. We do this out here, we get a numeric value now here. So we get this is now equal to 4.98 times 10 to the negative third, and we do our unit analysis out. This comes out in inches as we'd expect. So the next thing that we want to do is take this information and go to equation 17.5c, because what we're looking for is our critical shaft speed. And this is our equation we're going to use to relate to that. So now we head to figure 17.5 in our text. This is for shaft critical speeds. That's what we're looking for to solve in this problem. Take a look over here. There's A, B, and C. So you have your configuration, either one of these three, and with that configuration on the right, you have your critical speed equation. So we're not dealing with A, which is a single mass over here in the center. We're not dealing with multiple masses. We're dealing with C, which is the shaft mass only. So this is part C from figure 17.5. So we go over to the right for our equation for critical speed. We find now we have these relationships down here that give us our equation for critical speed. So this is equal to the square root of 5g over 4 times our delta st, which again our delta st is given to us as 5wl to the fourth over 384 ei. So with that equation for our critical shaft speed, we come back over here and got this approximately equal to the square root of 5g over 4. There's our delta st here, which again was equation 17.3, which was part C from figure 17.5. Plug in our known values here, 5. Well, we have our acceleration due to gravity, and again we're dealing with feet, so it's feet per second squared, so 32.2 feet per second squared. If we want to go from feet to inches, we multiply through here by our 12 inches in a foot, and then we come down here to our bottom 4 times our value here that we've already solved for here, our 4.98 times 10 to the negative third in inches there. Run this through, we end up, so N sub C is equal to 311 RPM for our shaft critical speed. Let's take a look at problem 17.2 now. In this problem here, they ask us to estimate the shaft diameter required to produce a critical speed. They give us the critical speed of rotation now of 250 RPM for an aluminum, so they tell us the material is aluminum here, shaft, with a total length, they give us our L value here of 1 meter, that carries a load at the center. So we have a center load here of 40 kilograms as shown in the diagram below. So again, here's a diagram below. Here's our aluminum shaft, total length, 1 meter, or L over 2 is 500 millimeters, L over 2, 500 millimeters. We have our center load right here of 40 kilograms. So now we've had a chance to go through our problem statement, look through our given schematic diagram. The next thing we want to do is go through everything that they give us, write out our variable names, our values, our units, how it relates to our problem, our given schematic diagram, what they're asking us to solve for, and any assumptions that we might make in the solution for our problem. So we do that, and the first thing we see, okay, we know our material here, it's aluminum, we're dealing with a shaft. They tell us in this case here, our critical speed is given to us as N sub C is equal to 250 RPM. We know we have a load, which is a center load here, giving us P is equal to 40 kilograms. And we have a total length of our shaft of 1 meter, or 1,000 millimeters, which units we want to deal with. So we have our simplified diagram here, center mass, 40 kilograms, aluminum shaft here, total of 1 meters. They ask us now to find the diameter of this aluminum shaft. So with this here, we want to make a couple different assumptions. The first assumption that we're going to make is that the bearing friction is going to be negligible, so we're not going to pay any attention to that. 2, the bearings supporting the shafts are accurately aligned. 3, the shaft is going to remain linearly elastic. 4th assumption, the shaft is simply supported, so we can see that here from our diagram there. And 5, the mass of the shaft is going to be negligible. So now let's take a look at our solution here. So the beginning part we want to do is come up with our governing equation. So in order to do that, what we're going to do is we're going to take a look at equation 17.1, and this comes from figure 17.5a in our textbook. So we're going to jump over there now to figure 17.5a. So now we take a look at figure 17.5. We're going to go to part A here for our configuration. So we can see here, this is the situation we have here. We have a single mass in the center here. We have 2 simply supported ends over here. We have our gravitational force acting down here. So we go over to the right now to our critical speed equation. We can jump down here to our N sub C that we're looking for, and 17.1a. So N sub C is equal to 30 over pi times the square root of g over our delta st. So now that we have this equation from figure 17.5a and equation 7.1, we can do is we go down and write it out here. What do we know? Well, again, we have this N sub C for critical speed is equal to 30 over pi times the square root of g over delta st, where we have g is 9.8 meters per second squared, and we're given our critical speed for the shaft in the problem statement of 250 RPM. So we can plug these values into this governing equation here. We end up with 250 is equal to 30 over pi times the square root of 9.8 over our delta st here. We can rearrange and solve, so we divide both sides by our 30 over pi, so we end up with 250 pi divided by 30 is equal to the square root, or 9.8 over our delta ST here. So then we can square both sides of this here, 250 pi over 30 squared, get rid of the square root on this side, rearrange it, solve for a delta ST, 9.8, all over divided by 250 pi divided by 30 squared. We end up with a value over here now of 0.0143 meters. So now the next thing we want to do is find what this maximum deflection is, our delta sub ST here. So we head to Appendix D1, our shear moment and deflection equations for simply supported beams. Now we go through all of our options for what the simply supported beams are. We have our concentrated center load, concentrated load at any point, uniform load. So what we have is case 1 here. We have a concentrated center load. We can see here's our center mass right there. There's our 2 supports on either side. We can see our maximum deflection at the center there. So then we go over to the right. We don't really care for this problem about the slope at the ends or the deflection at any point X. We care about the maximum deflection at the center. So we go with this equation here, PL cubed over our 48 EI for our max deflection. So from that Appendix D2, we now have our equation for the maximum deflection for a concentrated center load of a simply supported beam. So our delta ST is equal to PL cubed over 48 EI, where we realize we're still going to need to get our E value here. So that'll be the next step, is we're going to go to Appendix C1 for aluminum to look up our E value. And when we do that, our E is equal to 72 times 10 to the 9th pascals. So let's take a look here and head over to that Appendix C1. So here's Appendix C1 in the back of our book, the physical properties of common metals. So we can take a look at all the metals we have here. We come down till we see what we have given our problem statement. We're dealing with aluminum here. We're looking for our modulus of elasticity. We're in units of pascals here, so we have 72 gigapascals for our value for the modulus elasticity of our aluminum shaft. So now with this value for modulus elasticity for aluminum, we can go back to our maximum deflection equation from 17.1. So again, this here was our PL cubed over 48 EI, where now, what do we know? Which of these variables in this equation do we have information about? We have our load given to us as 40 kilograms, so it's a mass. We can multiply that by the acceleration due to gravity. We end up with 392 newtons. Our L is our length of the shaft here. This was given to us as 1 meter. We just looked up our modulus of elasticity, 72 times 10 to the 9th, and we're dealing with pascals. And our deflection we looked up here was 0.0143 meters. We can put all of this information back into this equation here. So 0.0143 for our deflection is equal to 392 times 1 to the 3rd, all over 48 times our E value here of 72 times 10 to the 9th. Our only unknown is our I. We can rearrange, solve this equation for I. We find that I is equal to 7.93 times 10 to the negative 9th meters to the 4th, where units check out. So now we want to head to Appendix B1A to figure out our relationship for this moment of inertia related back to our shaft diameter. So we go here for our properties of sections, go down to the shape of our shaft here, which is a circle here with diameter d. Come over here to the right for our moment of inertia. Our I is equal to pi d to the 4th over 64. So we'll use this relationship to back out our diameter of the shaft. So now we have the relationship and equation for our moment of inertia from Appendix B1. We can start plugging in our known values. We've already solved, we know that we have a value for a moment of inertia of 7.93 times 10 to the negative 9th meters to the 4th. So we can rearrange this equation and solve for d. When we do that, we can take multiply both sides of this given equation by 64. We end up with 64i is equal to pi d to the 4th. Then we rearrange this here, solve for d to the 4th with the pi on the other side. D to the 4th is equal to 64i divided by pi, where d is equal to the 4th root now of 64i over pi. So now with this here, we can plug in our value for I into this here. We find that d is equal to the 4th root of 64 times 7.93 times 10 to the negative 9th over pi. Solve this, plug it in. D is equal to 20 millimeters.